This question belongs to engineering mathematics subject and the topic is sets and relation. So the question states that every infinite cyclic group is isomorphic to the infinite cyclic group of integers under addition. We have to tell whether it's true or false. So the definition of infinite cyclic group states that let us suppose we have a group G, then it can be represented as G equals to A, where as it is a cyclic group, so it means that for all the integers k belonging to z, it will have all powers of k, like it will have a power 0, a power 1, a square. So this is infinite cyclic group, and even for the negative integers. Now let us define a mapping phi. So this phi will be from integers to this group G, and we can define phi of k as a to the power k. Now, as given in question, we have to prove that phi is an isomorphism. So first of all, we will use a p-proved statement that we have proved over here. It states that from a mapping from additive group of integers to the powers of group, element is homomorphism, then phi is a homomorphism. I will tell you the proof of this later on. Now, for the second one, assume that we have to show that phi is a surjection. So how we can show that? As we know that G is a cyclic group, it has been written over here, then every element of G is a power of A, as we have proved over here, for some A belonging to G. So if an element A belonging to G, then we can write that element as, let us suppose we have some element X belonging to G. Then there must exist some K whose raised to the power equals to X. As it is a cyclic group and X is an element of the group, then there must be some integer K whose when A is raised to the power K, we will get X. And by the definition that we have defined over here, we can say that phi equals to phi of k. And if it is a phi of k, then we can write it to be a to the power k. And we know a to the power k equals to x. Thus, phi is a surjection. Now we have to prove that phi is an injection, like it is 1, 1. So how we will do is that, like suppose we have m and n belonging to the integers, and then let us suppose m is not equal to n. Then we already know that if m is not equal to n, then a to the power m won't be equal to a to the power n. Like we have 2 and 3, then a square is not equal to a cube. So thus it is an injection. Phi is an injection. As we have proved that phi is an injection, we have proved that phi is a surjection and phi is a homomorphism. We have proved over here. I will show you the proof. Thus phi is an injective surjective homomorphism. Thus, we can say that every infinite cyclic group which is G is isomorphic to the infinite cyclic group of integers under addition, which is what we have to prove. So this is true. Now I will show you the proof of this one, like uh, from mapping from additive group of integers to powers of group, element is homomorphism, then phi is a homomorphism. Let us suppose that we have a group G0, then an element G belongs to the group. Then we can denote z comma plus with the additive group of integers. This is basically the theorem and this is the proof for it. Then we can define phi of g to be from z positive to the group. We are mapping define as, like for all the integers we can write phi of g of k to be g to the power k. It's a mapping which has been defined for z plus to the g0. Then we have to prove that phi of g is a homomorphism. So how we will prove that? Suppose we have two elements k and l belonging to integers. By this definition, we can say that as k and l belonging to, then we can write that phi of g of k plus l. What will be? It will be, according to the definition, it should be g to the power k. Here g is g and k is k plus l. So it will be equal to g to the power k plus l. And we can write it as g to the power k into g to the power l. And we can also write it as phi of g of k into phi of g of l. Thus, we can easily say that it is also a homomorphism. Thus, it is a surjective homomorphism and an injection. Thus, every infinite cyclic group is isomorphic to the infinite cyclic group of integers under addition.